allow me to start this session off by introducing you all to the concept, or rather, reintroduce you all to the concept of micromaps. So, to start things off, let us have a quick look at what I will actually present. In short, I have three main topics that I want to go through. And they are a quick overview about micromaps, and of course, opacity micromaps in particular, including a new micromap indexing algorithm. Then we will proceed through to discuss our main contribution in this paper, a new method for compressing micromap data by converting it into a densely packed tree format. But more on that in a little bit. Then we will round things off with a frame time performance evaluation of the above format, as well as many other formats used to perform opacity testing, including the official micromap formats that are now accelerated on hardware on modern NVIDIA GPUs. But without further ado, let us jump straight into the topic and talk about the micromaps themselves. What exactly is it? In short, it really is as simple as an array of values that has been mapped onto fixed sub-areas of a triangles that are specified by a space-filling curve. In theory, we could actually assign any kind of data to these particular sub-triangle faces. But for opacity micromaps in particular, we only care about 2 or 4 values. Consequently, these values only occupy either 1 or 2 bits each. Hence, the opacity micromap is typically handled as a type of bit string. And semantically, the values it contains are mostly self-explanatory. Fully transparent or fully opaque means that that particular sub-triangle face is either completely opaque or transparent in a ray tracing context, whereas unknown values means that we should use some other method to perform the actual opacity testing. For instance, by calling the AnyHit shader in the ray tracing pipeline and looking it up in an alpha texture. Additionally, these values also have a fourth value to allow you to convert it back into a 1-bit state. For instance, when you want to reuse a particular micromap in an algorithm where you don't actually want to call an AnyHit shader, such as when you are using shadow rays. Starting from the beginning, though, micromaps were originally invented in order to improve the performance with these AnyHit shaders. Simply put, by using a little bit of extra memory as input to the ray tracing pipeline, you could improve performance by reducing the number of times you would actually have to call the AnyHit shader by around 30 to 40%. And this concept has remained more or less constant in the current form of opacity micromaps that have found their way into the Vulkan and the DirectX API. The main difference is simply how the subtriangles themselves are ordered in the final bit stream, which you can see in these examples here. In the original format, the triangles are ordered in strips, going from the W coordinate in the left corner, going towards the V coordinate at the top. Whereas the current format walks across the subtriangles themselves in a bit more even fashion, very similar to how the C-curve orders tiles. One notable consequence of this, however, is that the original format is technically more granular, as each new subdivision level only really adds another strip. However, the negative part of this is that similar to data stored in row or column order fashion, this could lead to a somewhat unbalanced caching behavior depending on how you would actually access the micromap itself. And this then naturally begs the question, how would you actually look up a value in the micromap? Which, as if by coincidence, leads us to our first contribution. A new algorithm to kind of explain this mapping of barycentric coordinates to a micromap index. So, starting from the beginning, you have your triangle, and then you divide this at each of the midpoints, at the exact midpoint, thus forming 4 new subtriangles, which I have taken to calling the left, middle, right, and top subtriangles, which are also indexed, as you can see in the corner there. Then, by using a little bit of geometry, we can then derive equations to link together these midpoints and the vertices. And furthermore, we can express each vertex and midpoint using barycentric coordinates. And with a little bit of substitution, we can then find expressions that lets us use the original barycentric coordinates to update them again to any of the particular subtriangles. And we could then use that and repeat it recursively to any desired subdivision level to find the particular index of the particular subtriangle face index that we're interested in. There are a few more details to this though, but those details only really apply to the literal edge cases to ensure that rounding is correct. So if that's of interest to you, please see the paper for those details. Which then leads us on to our main contribution in this paper, the compression algorithm itself. As I worked with opacity micromaps, I found plenty of cases where large swaths of the map would contain basically the same value. Some examples you can see here from this text, from this small texture atlas from our good old sponsor scene at 3 subdivision levels. As such, I looked at the indexing mapping algorithm from before and thought, you know, wouldn't it be a good idea if we didn't have to go all the way down through the call stack to the subdivision level that was chosen to actually find that value, if we know that all of the values beyond a certain level is going to be exactly the same? That is, couldn't we have some kind of marker that tells us that you're not going to be able to find anything new beyond this point? And that is more or less what I did. I converted the micromap into a kind of 4-way tree structure, where each node represents the area of all underlying subtriangles, effectively mimicking the call stack of that previous indexing algorithm. And of course, as we've already seen in a few earlier sessions today, there are a couple of ways of representing such a tree. We could do it implicitly in an array, very similar to how we typically represent binary tree, or by using pointers. Storing the tree implicitly would be ideal, of course, because then we don't need any extra data. However, the trees that we are going to handle are typically not going to be balanced, so this would potentially lead to a lot of waste storage. Pointers, of course, could handle this particular aspect better, but at least for opacity micromaps, where the values we care about are so small, bringing pointers into this felt like a step in the wrong direction. However, by using a type of data structure referred to as a succinct data structure, we can store this tree in an almost optimal way. And one way of creating such a structure is by traversing the tree in depth-first fashion, setting a bit to 1 for every internal node that you pass through, or 0 for every leaf node. The resulting bit string will then uniquely represent the tree, and any node data that you have, such as the opacity values in our case, can then be tucked on at the end of this bit string, thus representing a micromap. So to summary, the way that I compressed micromaps are as follows. In a bottom-up fashion, combine any group of 4 subtriangles with the same opacity value to a single node, and then repeat this for all subdivision levels, forming our 4-way tree. And then repeat this for, and then encode that as a succinct bit stream, which you can see in this quick example. And for clarity, the tree and the opacity values, or data bits, are shown separately here, but of course that will be concatenated into a single stream. And even in this relatively small case, by comparing the bit string to the original and to the one we got here in the end, you can see that there's some potential for compression here. And if we were to look at the average result over all the scenes in this work, this turned out to be a very effective way at reducing the footprints of the micromaps, typically down to around 45 to 25% of the original size at reasonable subdivision levels. But in some extreme cases, such as for the new sponsor scene, we went all the way down to less than 1% of the original size, or expressed another way, compressed 110 times. However, we cannot just compress the micromaps. we also need some kind of way of looking up values from this new representation. And we can do that as follows, starting from the root node. After intersecting a triangle, represented by this dot on these slides, we need to figure out the index of the child that we need to visit, as well as update the barycentric coordinates to that particular subtriangle. And both of these things can readily be extracted with a single step of the indexing algorithm that I presented earlier. And this number then, this child index, becomes a kind of a counter. We need to step this number of bits into that bit string that represents the tree to find the next node that we should visit. However, if we are to encounter an internal node before this counter is 0, we need to also pass through all of the children owned by that node as well, as you can see here in the example labeled I on these slides. Or, in other words, we need to increment our counter by 4. Finally, when the counter is 0, we have found the node we want to investigate. And if the bit value of that, and the bit value in that tree string is 1, we need to repeat the above procedure, effectively going deeper down into the tree. And if the value is 0, we are done. And we are done, and the number of leaf nodes that we have passed until this point, that is, the number of zeros we passed through, is the index into the trailing bit string where we will find our opacity value. And with a method for looking up the values, we obviously need to compare this against some other ones. Thus, we have looked at the frame time performance, and in total investigated 6 different opacity algorithms. And they are micromaps themselves, but emulated in software using a small framework running in a any-hit shader, the succinct tree encoding, or the succinctly tree-encoded micromaps that I just described, as well as Vulkan-based micromaps built using the fast build and the fast trace flag, very similar to how acceleration structures are built. And then we also compare this against using a kind of bit mask, where each bit in the mask represents a pixel in the original texture, as well as the original alpha texture, to see how all of them compare. And in all cases, we test out both the 2-state version and the 4-state mode of micromaps to see how they differ. And perhaps a little bit arbitrary maybe, we also lock the subdivision levels to a fixed value for each evaluation. And as you can see then, for 2-state micromaps, this will actually determine the final look of the scene. But if you at least use any hit shader that looks up the alpha texture, you will not really see a difference when using the 4-state mode of micromaps, typically because it's just a performance knob in that case. As for the scenes we tested, micromaps are really only used in scenes with loads of alpha masks. So I chose the following scenes to try out all of these methods, which includes a decent sampling of old and modern content, as well as several orders of geometric complexity. And as I hope you can see from these images, I only really used a quite simple refining ambient occlusion rendering algorithm to keep things simple. This, however, also means that more complicated shading algorithms would likely benefit a lot more than what these results are showing. But that is out of the scope of this paper. And thankfully, we don't really have to look through reams of data to discern any particular pattern. Practically all plots have roughly the same shape, and we can roughly see the following. Using micromaps, software or hardware-based, is in general better than using either bitmask or textures, but not always by a large margin. And for software micromaps in particular, you can get a bit of a mixed bag of results. Sometimes you can lose as much as 30% of your frame time, but in other times you can gain as much as 16%. So it's really up to the user to make sure that they are applied properly. Whereas for a 4080, where you have hardware acceleration for micromaps, you will only ever lose, at least in these test cases, lose as much as 2% of your frame time, whereas you can gain as much as 29%. And unfortunately, the tree lookup algorithm that we invented only really performs okay for the first 3 or 4 subdivision levels. After that, it basically scales out of control, something that I will get back to in a bit. Interestingly, I was expecting the fast build and the fast trace to perform basically equivalently. However, there is a noticeable delta between them for some reason that you can see in the red and the orange lines. However, I don't know why that is. If someone from NVIDIA would like to speak up, I would be more than happy to hear it. And if we change things around a little bit into a somewhat easier scene, a single twig from the new sponsor scene. And here we can see a bit more of an interesting pattern. Although do note that I have removed the tree results in this particular plots in order to make things actually visible. And the most notable part here is that for a 3080, you will only ever benefit when you're using over using textures in a very small region, again, around 9 subdivision levels. After that, you even increase performance again, you reduce the performance again. However, do note the axes on these plots. The ranges are relatively small, all things considered, and the scene itself is a bit unrealistic. Which then brings me back to the tree method itself. Why does it perform so poorly? With the data packed so much more densely, surely caching should really help it, or at least make it comparable to the other methods. And I believe the main issue is this. When we want to find one of the rightmost children in a tree, we end up having to scan through all of the intervening subtrees, as seen in these examples. This is fine when the tree is relatively small, but is not really acceptable when the tree gets bigger. On average, it almost quadruples the number of bits that needs to be scanned when you add another level to the tree. And this is obviously problematic for something that should be comparable to an instant lookup, similar to a texture fetch. So how will we fix this in the future? A tree-based structure do seem like a good fit for compressing micromaps, but this initial lookup algorithm requires a bit of rework to be practical for larger maps, or at least to make it feasible to realize in hardware along with the rest of the ray tracing pipeline. Thankfully, there are numerous ways of restructuring tree, one of which is at least bound to be more practical. Also, there are currently only 2 types of micromaps out there, opacity micromaps and displacement micromaps. But there seems to be at least some ongoing work out there to create several other types of micromaps to store colors, normals, or similar data. So it would be interesting to see if such attribute micromaps could be compressed using similar techniques. Further, I only really considered lossless techniques in this work to make sure that everything matched the original micromap. But it could be interesting to see what happens if you allow everything to be lossy, to provide some kind of approximation for level of detail for faraway objects, or something similar. And interestingly, the indexing algorithm that I presented in the beginning is actually very generalizable. The same basic approach could really be used for a number of different shapes. So investing in that further could also lead to a number of interesting applications.
Gustaf, 2 minutes.
But to wrap things up, as a part of this work, we have done the following. Provided an arguably more descriptive algorithm for mapping barycentric coordinates to micromap indices, and used said method to create a compression algorithm for micromaps based on succinct trees, which is capable of reducing the memory footprint by more than 110 times. We also evaluated the frame time performance of this method, quickly realizing that while the method works, or in its practical for small maps, it is not useful for larger ones in its current form. And finally, the result was compared against various other methods, as well as the official Vulkan opacity micromaps, which itself showed a performance uplift by up to 29%. And with that, I think it's time to conclude and open up for questions, and hopefully, of course, some answers.
Okay, we've got a time for a couple of questions. Go ahead. Alex.
Is mip-mapping possible with your approach?
Repeat the question.
Oh, the question is MIP mapping practical or useful with this approach?
Yes.
I don't know. I think you could do some kind of mip-mapping strategy with it, but I guess your question is more, is it useful for the tree? I think you could try to map some kind of MIP level to the various hierarchies of the trees and use that, but that is not something that I have looked into at the current date.
Thank you. Over here.
I will yell. For your succinct representation of your triangle, it's all linear representation. Have you tried Morton codes or some sort of seed-filling curve?
Oh, the question is, have I tried using Morton codes or something like that in order to traverse my tree? Is that your question?
For representation, yes.
I have not tried that. The thought didn't really occur to me, as the original micromap is actually some kind of C-curve order thing. But it could be something interesting to investigate as well.
Then Alex.
Just a comment on the selection of a single twig. Do you think that's a representative for a game when you only have basically all the arrays hit something that has none of bait?
I would say that is not, is the twig scene that I showed you before a representable example? I would say that that is not really the case. It's mostly used to see some kind of pattern and see how the actual hardware behaves under those circumstances.
Good. I think we have time for one more question, if any. Okay, I've got one for you. What are some cases where we use any hit shaders but where OMMs don't work well?
I actually prepared an example of just that. Perfect chef. This is a very good example, taken directly from the San Miguel scene. Basically, you're in one of the corridors behind the scenes with loads of trees using opacity micromaps. However, almost all of them are occluded, but when you're tracing your race, you're going to have to call the NH shader anyways. So this is a case where you can actually lose quite a bit of performance, but mostly only for software-based approaches or for the 3080 in this case. For hardware ones, you barely see the performance hit at all.
Got it. Thank you. Okay, let's thank Gustaf and Michael one more time.